A star is actually a free-floating thermonuclear fusion reaction in space, constantly pushing out energy and radiation to avoid gravitational collapse. And it's really not avoid, just postpone, because fusion only works as long as you have atoms to fuse, but gravity never relents. And that's why it always wins. After the last fuel has inevitably been fused at some point, the star sheds its outer layers, and the remaining core collapses to a white dwarf, which will also be the fate of our Sun in a couple billion years. And after that, a single number will decide whether the white dwarf will remain stable or collapse further, maybe even fully, to a black hole. The Chandrasekhar limit. A white dwarf is holding up against gravity mainly by electron degeneracy pressure, i.e. the quantum principle that prevents them from occupying the same quantum states. Calculated classically, this should give a star a stable equilibrium radius at any given mass. But the real white dwarf conditions are so extreme that the electrons actually approach the speed of light. And when you do the calculations relativistically, there is no more stable state beyond a certain mass. And this is the Chandrasekhar limit, about 1.4 times the mass of our Sun. Beyond this point, gravity wins again. This will either trigger a supernova or the white dwarf will collapse into a neutron star. And if the remaining mass in this case is above the Oppenheimer-Volkoff limit of 2.3 times the mass of the Sun, it will completely collapse into a black hole. Subscribe for more cosmology.